All right. In this video, what we're going to do is look at the multiplication of various scenarios between two different matrices and a scalar constant of -2. So our first matrix, A, is a 2 by 2 matrix. It has two rows and two columns. This is what we would call the square matrix. And this matrix B is a 1, 2, 3 by 1, 2 column. This is a 3 by 2 matrix. And another matrix that we are going to introduce later is this matrix here. This is called the identity matrix. We'll spend a lot more time talking about the identity matrix later on, but for our case, the identity matrix is a square matrix with ones along its diagonals. And it looks in that one. That column should be more aligned, but you get the idea, I'm sure. All right, so let's look at the product of A and B. So our product of A and B, we're going to have 1, -3, 2, 1. We're going to multiply that by the 3 by 2 matrix of 0, 7, 1, 6, -3, 2. Okay. So as I said, this matrix is a 2 by 2, and this matrix is a 3 by 2. So to define matrix multiplication, the first thing we have to do is to make sure that it's actually you're actually able to multiply the two matrices. And you can tell by the dimensions of the number of columns in the first element or first matrix by the number of rows in the second matrix. And if those two numbers are not equal, then this matrix product does not exist. D&E is common notation for it does not exist. It's not defined that direction. So let's look at the other direction then. Is B times A defined? Based on what we had just done in the previous one, you could pause the video now and see if you could guess if this product is defined or not. And if so, how would you find its value? If not, then we're pretty good. And this is a pretty easy product or problem to figure out. So let's go ahead and assume that you've taken the time to do that. And this is 3 times 2, and this is 2 times 2. And if we look here, okay, these are equal. The number of columns in the first product and the number of rows in the second one are equal. And so we can multiply these elements out. And so the way to think about this is that you're going to multiply this row times this column, and then this row times this column to produce the two elements. Okay. All right, so let's go ahead and do that. So I'm going to write each of them out individually. I'll write it out over here, just continue, and then I'll continue this one below it. Okay. So the first element is going to be 0 times 1 plus 7. 0 times 1 plus 7 times 2. Okay. And then the second element is going to be 0 times -3 plus 7 times 1. Okay. So that'll be the first row, and the second row will be 1 times 1 plus 1 times 1 times 6 times 2. Okay. And then the fourth element, or the first of this product matrix, is going to be 1 times -3 plus 6 times 1. And I'm hoping you're starting to see a pattern in the way that these are showing up. -1, 3 times 1 plus 2 times 2. Okay. And then over here, we're going to have -3 times -3 plus 2 times 1. Okay. And then all we have to do now is do the products and add like terms together. So if we do that, then we get, this is 0 plus 14. This is 0 plus 7. This is 1 plus 12, 13. -3 plus 4, so that's 1. This is +9 plus 2, so 11. -3 plus 6, so 3. Okay, and so then the product of uh, this result is B times A, sorry, this result. And you'll notice something interesting. We have 1, 2, 3 rows and 2 columns. So if you look back here, you should notice that that then is the same exact numbers as we would see there. And that's no accident. Whenever you multiply two matrices together, the inner values, if you will, the columns of this matrix and the rows of this matrix tell you if the product is able to be multiplied, and the outer one will tell you how big that resulting product is. So that's really nice to check. If you get a matrix that doesn't fit those numbers, may have done something wrong. Okay. All right. Let's go ahead and look at this particular one here then. And so we're going to multiply the scalar -2 times every element in A, and then we're going to add that to our identity matrix I. All right, so C times A plus I, and so we're calculating. So C was -2, and A was 1, -3, 2, 1. And notice that I'm writing out every step. When you are working on these, I would highly recommend writing out every step just to kind of get used to where everything's coming from. But as you get more comfortable with it, you may start to find shortcuts that make the whole process a lot maybe less time consuming or less volume of writing or whatever. Anyways, okay, so I'm going to multiply this into each of the terms. And so in doing so, I get -2 times 1, that's -2. -2 times -3, that's negative. And then negative, I get +6. -2 times 2 makes that a -4. And -2 times 1 makes that a -2. Okay. So I'm going to add to this the identity matrix. And so multiplying by a scalar, you multiply each element in the matrix. Adding, as we saw earlier, is element-wise, meaning corresponding elements, corresponding parts add together. So in this situation, then I have -2 plus 1. That's these two elements, plus 6 plus 0. And that's sorry, but that's not a plus. 6 plus 0. I meant the plus for the 6. All right. 6 plus 0. Here we have -4 plus 0, and then -2 plus 1. Now, obviously, when I'm doing this, I don't usually write the plus zeros, but I just want to kind of show you element-wise how each one goes. I didn't show the multiplication of the -2 here because I was kind of demonstrating where they're coming from. So I hope that makes sense. Okay. Last but not least, combining everything together, we get -2 plus 1, that's -1, 6, -4, and -1 again. Okay. So in this situation, the scalar multiple of -2 times A, and then adding the identity matrix gives us this resulting matrix. Okay. All right, we're going to look at one more example, one more idea here. Going back to our matrix B, we talked a little bit about this idea of a transpose of a matrix. And so I'm going to use B to kind of illustrate the point. I think it's a little bit easier to see in a kind of a rectangular matrix versus a square matrix. So in this situation, this is B. And we want to find B transpose. And then we're going to do some fun stuff with B transpose and multiply them together. Okay, so if we recall the definition, if B is equal to Bij, where I is the ith row and J is the jth column, then the transpose of B is going to invert or switch the rows and columns. And so now each of the J columns now become J rows, and each of the I rows now become I columns. Okay? So that means for this one, this is the first column is now going to become the first row. So 0, 1, -3. This is the second column. It is now going to become the second row. So 7, 6, 2. And so this is the transpose of B. Okay. So the last thing we'll want to look at is B times B transpose and B transpose times B. So let's look at these products and see one more thing and see maybe if we can kind of hypothesize or make a pretty good conjecture from this calculation as well. Okay. All right. So B is 0, 7, 1, 6, -3, 2. And B transpose is 0, 1, -3, 7, 6, 2. Okay. This is a 1, 2, 3 row by 2 column, and this is a 1, 2 by 3. So notice that these two do line up. So this product is defined, and our product is going to be a 3 by 3 matrix. Okay, just real quick, let's look at B transpose. And that's 0, 1, -3, 7, 6, 2. Is this product well defined? Pause the video and calculate it for yourself. All right, so when you've had a chance to do that, let's go ahead and dive in and see if you were picking up the same result. Okay, so this is a 2 by 3 matrix, and this is a 3 by 2. So since those two are equal, the product is well defined, and look, this product is going to be a 2 by 2 matrix. So if I asked, are these two equal? Well, the size of the matrices matter, and just on that alone, you could say no, because this is producing a 3 by 3 matrix. That's 9 elements, and this is producing a 2 by 2 matrix. This is 4 elements. So this one is much bigger than this one. So clearly they're not the same. So in general, as we saw earlier, right, A, B, and BA, one didn't even exist, and the other one I gave us a matrix. The matrix multiplication is the notoriously famous example of a multiplication scheme, if you will, that is not commutative, meaning order is important. You can't switch the order and expect the same results, unlike our more familiar regular numbers or real numbers or even imaginary numbers. Okay, all right, let's go ahead and compute this product just to make sure that we get, I'm not going to do the whole thing, but I'll try and give you a few elements of it so you can kind of get the sense of how each of the elements are formed. Okay, so for the very first element, you're going to take this row. Sorry, I'm putting up two things, this row and this column, and multiply them together. So 0 times 0, 7 times 7. And so that would be this first row, which would be 49. Okay. And then for the second one, you're going to take this row and multiply it by this column. So 0 times 1 times 4 times 6. And you're going to add that together. So that's 42. And then the last one, you're going to multiply 0 times 3 and 7 times 2. So that's going to give you 14. Okay, so that's the first row. As you can see, then that's the first row. So then there's 3 elements. And so you're going to have 6 more elements to construct from that product. And likewise over here, what does it look like for a 2 by 3 by a 3 by 2? Okay, so you're going to take this row and multiply it by this column, and that will be our first entry. Okay, so 0 times 0 plus 1 times 1. So right now we have 1 plus -3 times -3, so that's 9. 9 plus 1 is 10. Okay, so that'll be our first one. Here, we're going to take this row and multiply that column. That'll be our second entry. So 0 times 7 is 0, 6 times 1, 6, plus the -6. So that's actually going to be 0. Okay. And then so you follow the same thing. This row times this column will give you this element, and this row times that column will give you that element. Okay. So clearly not the same size, definitely not equal in terms of the commutative property. But now you know how to construct the transpose. You know how to multiply two matrices, and when the product is defined, and when the product is not defined. And you also saw how multiplying a scalar times a matrix, and then adding the two matrices together. By the way, if this was a subtraction, it's kind of like the multiplying the scalar by -1. So when you would be adding all of these elements together, you would have a minus sign in each of those elements. Oh, here, sorry. I was like, where did I cut it? So instead of being a plus here, these would all be minus signs because you'd be subtracting. So it's actually like multiplying by -1. Subtraction and division in matrix algebra are more defined in terms of additive inverse and multiplicative inverse than they are by division and subtraction that we're more familiar with than the real numbers and stuff. All right, I hope that was helpful. I'll see you next time.